Welcome to this next lecture on fundamentals of acoustics. We will look at the sound field inside a cylinder. We have started looking at interior acoustics using the interior KH integral, and we looked at the rectangular box in the previous class. In this class we will look at the interior of a cylinder. Okay. So, what is this? This is a cylindrical enclosure of length, let us say Lz, of length L, and a radius of A. Okay. So, we will take this to be the Z axis, okay, and this to be of course R, and this to be theta. Okay. So, now the PDE, the acoustic PDE in cylindrical coordinates. How does it look like? It looks like this: 1 over R del R, R, let us say del P by del R, plus 1 over R square del 2 phi by del 2 P, del 2 P by del phi square plus del 2 P by del Z square is equal to 1 over C square del 2 P by del T square. Again we will use the method of separation of variables. Okay. So, we substitute for P R. Okay. So, this angle is phi instead of theta, let us call it phi. P R phi Z T, we substitute R of R, phi of phi, Z of Z, and T of T. If I substitute this into this equation, okay, so what I now get is phi Z T 1 over R d by dr R dP, R d R by dr plus R Z T d2 d phi square of phi plus R phi t d2 dz square of z plus is equal to r phi z d2t by dt square. Now if I divide the whole thing by r phi z t, okay, so I get 1 by r d by dr r dr by dr plus 1 by phi square here, 1 by r square d2 phi by d phi square plus r plus 1 by z d2z by dz square is equal to 1 over t d2 t by dt square. Okay, again we'll give this a negative and a real number. So it's a negative real number. Okay, so we take up one by one, we take up the time equation. One over t d2 t by d t square is equal to minus k square. Missed out a c also. C square okay. So what we have now is d2t by dt square plus k square c square t equal to 0, and this is omega square. Okay, omega square. My solutions t of t, I can take them as some a tilde e to the power j omega t plus b tilde e to the power of minus j omega t, or a cos omega t plus b sin omega t. So that's the t solution. Okay, so now this is equal to minus k square. I suppose you see why it has to be a constant. Is a function purely of r, it's a function purely of phi, it's a function purely of z, it's a purely function of t, and therefore it has to be a constant. Okay, we have seen this in the rectangular Cartesian case. Okay, so now the other remaining equation, what we have is 1 over small r capital R d by dr r dr by dr plus 1 over r square phi d2 phi by d phi square plus a k square is equal to minus 1 by z d2z by dz square. And this we write as a kz square, a positive number. Okay, again similar reasons. Okay, I am not going to repeat. So if we consider just the z equation, I get d2z of z by dz square plus kz square z equal to 0. Okay, and so this now has the form, let's call it c cos kz z plus d sin kz z. Okay, so that's z equation now. Okay, so now what happens? The remaining I have, okay, this and this now. So what I will do is rearrange again, okay, rearrange the remaining part with this term and this term. So what I do is first multiply this equation by r square, this by r square, and adjust term. So I have r by r, d by dr, r dr by dr plus k square minus kz square into r square is equal to, this I take to the other side now, minus 1 by phi d2 phi by d phi square. Okay, so again this now is purely a function of r, this a function of phi alone. So then again it has to be some constant, call it m square. Now if we look at these two, I have d2 phi by d phi square plus m square phi of phi equal to 0. Okay, and this has the solution phi of phi given by, let's say, e cos m phi plus f sin m phi. Okay, now let me just say here that this m has to be an integer. Okay, why? Because we have the cylinder and let's say phi goes in that direction. Now let's say this is my phi 0, I go around once and come back here, phi becomes 2 pi, but the physical location is the same, so the function or the physical quantity must be same. Okay, so if phi goes from 0 to 2 pi and this function has to be same, m has to be an integer, otherwise it won't work. Okay, so now we have taken care of the phi equation also, and the remaining now is here, okay, which looks like r over r dr by dr plus r square over r d2r by dr square. I just opened out this derivative, then plus k square minus kz square into r square minus m square equal to 0. Okay. Now this k square minus kz square. Okay. So let's say within the cylinder the k acoustic wave number is in some direction k. Okay, in some direction. This is the k is the acoustic wave number. One shouldn't forget. Omega by c is k. We are working with the Helmholtz version. Okay. Okay. So now what we have here is this k is in some direction, and when I subtract kz, okay, then it takes out everything that is away from this plane. So the resultant is the in plane wave number. In plane wave number. We'll call it k r phi. Okay, k square r phi, where k r phi is the in plane wave number. So k r phi is the in plane wave number, kz is the out of plane wave number, and therefore the combination is the k acoustic wave number. Okay. So now what do we have here? We will rearrange this. We have 1 over r dr by dr plus d2r by dr square plus k square r phi minus m square by r square into r equal to 0. Okay, this is a Bessel's equation in cylindrical coordinates, and therefore the solution is a combination of cylindrical Bessel functions Jm first kind, mth order kr phi into r plus r2 cylindrical Bessel function of second kind kr phi of r. Okay, where this m index is the same as this m index. They are tied together. This m index is that m index. Okay. So now if we combine all of this, we have all the functions ready. So if I look at r, phi, z and t, okay, what I have is r1 jm of k r phi of r plus r2 ym k r phi of r multiplied by e cos m phi plus f sin m phi into what did I have, c cos k z z plus d sin k z z into a cos omega t plus b sin omega t. Okay. Now we have a rigid walled cylinder, that's what we are looking at. Okay, a cylinder of finite length where the walls are rigid. Okay, so if we look at the z part of the equation, it had said the solution were c cos kzz plus d sin kzz. This was z of z. Okay, so now it has to satisfy boundary conditions. Okay, so if it is rigid walled, then z dash of z, derivative of capital Z with respect to small z, is 0 for z equal to 0 and z equal to L. Okay, to just remind you, the equation was d2z by dz square, this is capital Z, plus kz square z equal to 0. It's exactly a Sturm-Liouville problem, okay, for those who are interested. It's a Sturm-Liouville eigenvalue problem. Okay, so now if I set z dash, what is z dash? First of all, z dash dz by dz is equal to minus c kz sin kzz plus dkz cos kzz. Okay, now first of all, this is 0 at z equal to 0. At z equal to 0, this is anyway 0. And z equal to 0, this is the right side is dkz equal to 0. If kz is 0, it becomes a trivial equation, trivial solution. So kz is not 0, but d is 0. So therefore, when d is 0, this term goes to 0. Okay, so let me see, z of z is equal to c cos kzz. Okay, now the other condition is at z equal to L. So dz of z by dz at z equal to L must be 0, which means d kz which means I have c kz sin kzz equal to 0, which means kzz equal to kz at L, kz L is equal to, let me call it q pi. Q goes from 0, 1, 2, etc. Okay, 0 is the trivial case. So now my kz, the wave number, is not a one, has many values. There are many values of kz which satisfy this boundary condition. Okay, many values of kz which satisfy this boundary condition. So my mode shape now, z of z is equal to c cos q pi z over L, and q going from 0, 1, etc. Okay. So kz has acquired a value and kz is many, so we will call them kz q is equal to q pi by L. Okay. So then if we now look at this function again, we have Jm and Ym, and let me just show you here. The Jm, the J0 behaves like this. It starts off at a non-zero value at r equal to 0 to, okay, and then it starts to oscillate, goes through zeros and then maximas and then zeros and maxima, oscillating and decaying. This is your J0, and J1s are also similar. J1, J2, they are all similar. Okay, they start off at 0 and start to oscillate, and they go through oscillations and decays. Whereas the y's, all of them start at infinity at r equal to 0. Okay, at r equal to 0, yms go to infinity. And therefore, if r equal to 0 is part of the domain, is included in the domain, then R2 has to be 0, because pressures do not go to infinity. Okay. If you are considering an annular region between two cylinders where r equal to 0 is not included, then you have to consider this Ym also. Okay. But we will be considering a hollow cylinder where radius 0 is included, the center line is included. So R2 will be 0, so only Jm will be part of my solution. So how does it look? The R phi zt looks like J1 of k R phi r, okay, Jm into E cos m phi plus f sin m phi into C cos q pi z by L into, what did I do here, A cos omega t plus B sin omega t. Okay. So that now takes care of the z direction. Now we have the r direction also. Okay. In the r direction, if we look at, we are only including the first kind Bessel functions. So let's say we look at J0, and J0 starts off 0 derivative with a maximum, goes through a 0, has another maximum negative, goes through a 0, has another maximum, and so forth. Okay. Now R of R was R1 Jm K R phi of R. Okay. In order to find R1, we need a boundary condition. So what is the boundary condition? Boundary condition is that R dash at A is a 0. Okay. Why? Because the cylindrical wall is rigid walled. This wall is rigid walled. And therefore R dash at A must be 0. That means Jm dash Kr phi at A must be equal to 0. Okay. That means if I look at J0 dash Kr phi A, where does it go to 0? It goes to 0 here, it goes to 0 here, it goes to 0 here, goes to 0 here and here. So if I plot Kr phi A, let's say, okay. So now we have tabulated values. We have tabulated values where J0 or the derivative J0 dash of Kr phi A go through 0. Okay. And therefore there are many Kr phi values. You can see there are many Kr phi values where the J0 derivative is 0, where J0 dash Kr phi A equal to 0. Okay. So essentially how would you interpret this? If this is the pressure, this is actually the J0 function, right? This is a J0 function which is Kr phi of R, like this. So let's say this happens to be the radius. This happens to be the cylindrical shell radius. Okay. Then at the wall you have J0 dash Kr phi A goes to 0. Okay. And let the radius be incremented or Kr phi incremented, so that Kr phi A is the next value. Then you have this situation. Okay. So the function goes through A0, the function goes through A maximum, the function goes through a 0, and the function goes to the next maximum Kr phi A the second, where J0 Kr phi A dash is 0. Okay. In a book these have been tabulated. The Bessel functions are not commensurate functions like causes and sines. So these values have been tabulated. So let's say J0 dash goes through 0 where? For m equal to 0, which is what we are looking at, the first value is of course 0. Why? Because the J0 derivative is 0 right at 0. So at k r phi a equal to 0, you get a 0, and this is the k r phi a value, k r phi into a value. Okay. Then n equal to 1, that is the next one. This value is 3.83. So at a value of k r phi a equal to 3.83, you have the next derivative going to 0. And where is the next one? This is n equal to 2. This is 7.02. Again, for a k r phi a value of 7.02, okay, 0, 1, 7.2, this is 7.02, is 3.83. Okay. So from the center to the radius, this is the r function, right. So it starts off at a peak at the center, it goes through a 0, it goes through a maximum at the radius. This is 3.83. Next, it starts off as the radius, it starts off at a peak, it goes through a 0, it goes through a peak, goes through another 0 and goes through the next peak, and this is at the wall of the shell. This value is 7.02. Okay. So now this is tied with cosine. This is tied with the cosine and the sine. Okay. So if m is 0, and we are going round phi also at the same time, so what this means is that there are no nodal lines. Otherwise, and this is axisymmetric, that is what it means. For m equal to 0, this is axisymmetric. So no variations along phi. Okay, that means no nodal lines, no diametral nodal lines. So no diametral nodal lines for m equal to 0. Nodal lines. Okay. If m equal to 1 now, if m equal to 1, let us see m equal to 1. Okay. So m equal to 1, then we are talking J1. Okay. How does J1 look like? J1 starts off at a 0, goes to a peak, goes through a 0, goes through a peak, goes through a 0, goes through a peak, and oscillates. Okay. So if m equal to 1, then the n equal to 0 value, the first value where it requires a 0 derivative, this value is 1.84. Okay. So this value is 1.84. Then n equal to 1, this is 5.33. N equal to 2, this is 8.54, and so forth. Okay. We are about running out of time, so I will close the lecture here for now, and we will continue along these lines in the next class. Thank you.